Can you please mute your microphone? So we will start today problems of chapter 3. We will start first by an example from the book to see how we can calculate the pressure variation along a streamline. So in this problem, consider the envisaged incompressible steady flow along the horizontal streamline AB in front of the sphere of radius A as shown in the figure. From a more advanced theory of flow past a sphere, the fluid velocity along this streamline is V equals to V0 times 1 plus A cube over X cube. We should determine the pressure variation along the streamline from point A far in front of the sphere until point B, which is on the sphere. It is given that x of A is at minus infinity, corresponding to an initial velocity V0, and at point B, B is called a stagnation point. The velocity at B is 0. Okay? So here, first, we should see what are the given. The characteristics of the fluid are very important to know which equation to apply. Okay? So first they told us that we have an inviscid. When they say inviscid, this means that the viscous effects are negligible. So when I draw the free body diagram of a small element of the fluid, I should not take into consideration viscous effects. Incompressible means that rho is constant. So I don't have variation of rho with position. Steady flow, this means that my flow is independent of time, so it's steady state. And I am interested in particular in streamline AB, which is a horizontal streamline going from point A to point B. What I know is that the velocity of A is V0, and since B is a stagnation point, VB is equal to 0. And they gave me the equation of velocity. We will learn together after how to find the equation of velocity, but for now, they just gave us the equation of velocity, function of x, and you can verify that this equation corresponds to the given conditions, because at A, x is minus infinity. If you replace here x by minus infinity, you will have this term will drop, and you have only V0 times 1, while at point B, as you can see in the figure, point B is, x of B is minus A, so x of point B is equal to minus A. So if you replace x of B in this equation, you will get 1 minus 1, which is 0, which corresponds to velocity at B equal to 0. So in this problem, we know the profile of velocity. We want to determine the profile of pressure. Whenever I need to correlate pressure and velocity, you should go back to the definition in the course material. What we did, we take in the course material a small element of the fluid, and we have considered the free body diagram of this element, putting all forces acting on it. As can be seen here, since it's inviscid, so no viscous effects, and in the course you develop the formula for inviscid flows, and it's steady, so we don't have a transient term. So if we go back to the course material, after applying the second law of Newton and simplifying by the volume, what you get is the following. The equation you got in the course is, I will write it here, okay? It's minus gamma times sine theta, and I will go back to the course material to tell you in which part you are working, minus, where theta represents the slope of the streamline at a certain location, minus del P by del S, where S is the coordinate of the streamline, equals to rho times acceleration along S, and the acceleration along S is replaced by V del V by del S. So it's equal to rho times V del V by del S. Okay, so this is what was developed in the course material. Now, in this problem, in this particular problem, what is S? So we are interested in which streamline? We are interested in the following streamline, which is horizontal. If you go back to your slides, when you did the analysis for a small ds, you considered a fluid element along ds. So this is ds, okay? And theta represents the angle between ds and dx. So what you did is ds can be decomposed into dx and dy, okay? And we said that theta represents the angle between the streamline at a certain location and the horizontal direction. So this is theta. Now in this problem, in our problem, the coordinate s is simply what? Who will tell me? What is s in our problem? We are moving along which line? We are moving along x-axis. Okay, so our coordinate is x. So in this equation, s corresponds to x, and theta is equal to what here? What is theta in this problem from A to B?
Isn't it 0?
It's 0. Very good.
0.
Yes, it is 0. So in our problem, as application here, in our problem, the streamline coordinate s. So along AB, if you want, because we are interested in streamline AB. Along AB, we have that the coordinate s is simply x, and theta is 0. Okay, so since theta is 0 degrees, so sine theta is 0, and the first term will drop. So we don't have this term here, will cancel out. This one, gamma sine theta is 0. So now if I replace in my equation s by x, what I will get is, so in my problem, I have here, so minus dp minus del p by del x is equal to rho times v dv over dx. Okay, so now everything is simple because I have v function of x. So all I have to do to determine my pressure variation along the streamline is to replace the v function by its value. Okay,
دكتور v dv by dx ولا dv by ds؟
ما هي what is ds? It's dx. Now we said that along AB, along
okay,
streamline
صح.
AB, s and x are the same. Okay, so you can replace s here in this problem by x because we are interested now in streamline AB. If you move along in another streamline, it will be different. Okay, so if you move along the following streamline here, no, it's ds, because for this case, for this streamline, the s variable is different than x and z. It's a new variable. Okay, but in particular for this one, everywhere s is represented by x because you are moving horizontal. And if you move along z, then s will be z. But if you move along a curve, you need to define a new coordinate, which is s. Okay, so now all we have to do is to replace v by its value. So as you can see, v is already function of x. What I still need to find is dv by dx. This is a simple mass formula, so we can derive it easily. You know that, so I can write here. So I am interested in finding dv by dx. Okay, so for dv by dx, equals to, you have v0 is a constant, so I will keep it. Okay, now you have the function, you have this function to derive. One is a constant, so when you derive it, it is 0. You have plus a cube over x to the power minus 3 يعني over x3, so it's equivalent to a3 times x to the power minus 3. And you know that when you derive, if I have x to the power n, if I want to derive it, it's n times x to the power n minus 1. Okay, so since I have a3x minus 3, the derivative will be minus 3a3 times x to the power minus 4. Okay, so when I derive, I get minus 3a3 times x to the power minus 4, which is equivalent to 1 over x to the power 4.
دكتور
Yes.
ما كان في دغري استعمل الفاينل برنولي equation قول انه it's constant البرنولي equal constant على A وعلى B واعمل calculate لل V وجيب ال P.
When you use Bernoulli equation, you apply it between 2 points. Okay?
Yes, A and B.
Yes, you want to apply it between any two positions. V, here, if you just apply between A and B, you get pressure at B only. You don't get pressure function of X.
Okay.
Okay? So Bernoulli is used in general whenever you want to apply between 2 points. But
to
here
get
they
it on
did,
one point.
yes, if they ask you find the pressure at B or find the pressure at a certain point, yes, of course, you will do this. But since they want the pressure variation, okay, so you need to find the function, you will do this. Anyway, you can apply Bernoulli if you want. If you want also another possibility, you can apply Bernoulli between any position A and any position X, and you will find P function of X. It's also a possibility. It's not wrong. Okay? But not between A and B. You should take any point. So you will say, I'll take any point in between. And I will call this coordinate, let's say it's X. So here I have V of X and I have P of X. But here they, so you find P of X and then you should derive, because they said find, if they tell you find the gradient of pressure, you should derive again. If they just tell you find the pressure function of X, so it's fine. Okay? So now, once you derive, any problem with the derivative? Once you derive, all you have to do now is to replace in your equation. So once I find dv by dx, let us see the calculation method. So first, as we said, we applied the equation, and the equation is derived from Newton law. So just you do Newton law for a small element of your fluid, then you simplify by the volume, you get the equation I wrote for you. Then you apply for theta equals 0, you get your relation. And now you derive V. So as we did, we derive V with respect to X. You get minus 3V0 A3 over X to the power 4. This is the derivative we did together. Okay, so this is our derivative. You multiply it by V, since we know that here in this expression you need minus rho V del V by del X. So once you multiply it by V, you will get the following function. If you do the expansion, okay, just you do the expansion of these terms, you will get the following relation. Okay, because here you have V0 and here you have V0, so it will be minus 3V0 square times this term times A3 over X to the power 4. Now, the next step is to just replace in this equation. So you replace V del V by del S in this equation, okay? And once you replace, you get the expression of del P by del X. So here del P by del X is given by the following formula. As you can see, this is the pressure variation along, this is the gradient of pressure along X. Now, if we want to get the pressure function, we need to integrate, okay? So if I need to find P function of X, all I have to do is to integrate this equation. And I will integrate between from what to what? From minus infinity, because the condition that I know is at minus infinity, okay? Or also, I can also integrate from X to B, because I know that, so I have two boundaries. I can work or with the boundary at A or with the boundary at B. If I choose the boundary at A, I will say that it is true that I can take the boundary at B. Who will tell me? So if I say at XA equals to minus infinity, what is my pressure? What should be the pressure at infinity? Very far from the sphere. What is the pressure very far from?
Zero?
Yes, if I'm considering gauge pressure, it's 0. And if I'm taking absolute pressure, it's P atmospherical. So since we are working, if we work in gauge, so P gauge, let us say, P gauge at A is 0, since it's equal to the atmospherical. So when they don't mention anything, so it's equal to the atmospherical pressure. Okay. Now, if I want to work with the boundary condition at B, what should I do? Do I know the pressure at B? So X of B is equal to minus A. Okay. But what is pressure at B? Do I know it? If I want to use it as a boundary condition, I should know the pressure at B. How can I find the pressure at B if I want to use it? What can I do? Yalla, who will tell me how to find the pressure at B?
Can we use Bernoulli's equation?
Yes, very good. We can use Bernoulli equation. But of course here, why to choose B if I already know the conditions at A? So since I already know the condition at A, I will directly take A as a point. But if they ask you to find PB, it's very simple. You can just apply Bernoulli between A and B. So to find PB, this can be found by applying. So we apply Bernoulli, okay, from between A and B, okay. What is the Bernoulli equation? We have, it states that pressure at point A, okay, plus half rho V square, half rho times V at A square, okay, plus rho G times elevation of A, okay. So I should take a certain, so here I consider this is the origin is at the center of my sphere, equals to the same expression at point B. So at point B I have P at B plus half rho VB square plus rho GZ of B. Now, since A and B are at the same elevation, okay, these two terms will cancel out. Rho GZA equals to rho GZB, since the 2 points are at the same level. Now I know that B is a stagnation point, so VB is 0, it will cancel out. So I will end up with, and PA, as you said, is 0. If we are talking as gauge pressure, PA is 0. So I end up with the following result, that PB is equal to half rho times V0 square, okay? And whenever I have a point where the velocity is 0, I say that this point is characterized by the stagnation pressure, okay? So now, when you write Bernoulli, what are your different terms? You know, when I say PA, this represents which pressure? So in Bernoulli equation, you have the following: P plus rho V square plus half rho V square plus rho G Z equal to constant. Okay, this is the Bernoulli equation. Now for each term, what is the definition of each term? What is P? P represent what? You remember from the course material. This is called static pressure. Okay, so P represents the static. Why we say it's a static pressure? Because this pressure is just due to the fluid, to the energy flow of the fluid. It's not related to it's a potential energy in the fluid. If it is in motion or at rest, you will have a static pressure. Okay. However, when your fluid is moving, in addition to the static pressure, you have another, if you want, type of pressure called dynamic pressure. So it's half rho v square, okay, is named dynamic pressure because it's due to the motion of your fluid. So this is called dynamic pressure, okay, and rho gz is called the hydrostatic pressure. This is the pressure you are familiar with that we did in previous chapters, okay. So when your fluid is not moving, you don't have the dynamic pressure. Then you will have the if your fluid is at rest, you end up with P plus rho gz equal constant, and we go back to the previous chapters we did, okay. So this is the hydrostatic pressure. Okay. Now, if we continue our problem here, just let me check your charts. Okay. So, if we continue here, we want to find the expression of pressure. So we will integrate from A. We will choose A because we already know that P at A is 0 gauge. Okay. So we will integrate from minus infinity to any position X of interest. So if we do the integration between minus infinity and X, okay, we can just get the corresponding value, because let us do it in a simple way. This is del P by del X here, okay. This is your function. It seems a little bit complex, but it is simple. So if you divide it into two terms, what is del P by del X? You have that del P by del X equals to, I will split it into two terms. Okay, so the first one is 3 times, or if you want, I will keep this as your constant. So I will call it constant A or constant F for example. Okay, constant F. This is the constant F. Okay, so this is F. It's a constant term. So, and here I will divide this into two parts. I have 1 over x to the power 4. So 1 over x 4, okay, plus a cube over plus a cube over x to the power 7, okay. And we know that to integrate a function, so it's like here I have x minus 4 and here I have a 3x minus 7. I know that if I have x to the power n, if I integrate, so by integration, I get x to the power n plus 1 over n plus 1, okay? So all I have to do is to apply the rule here, having for this function, for the first function, n is equal to minus 4, and for the second function, n is equal to minus 7. So it's simple math, and I can get the integration. If I integrate and I replace the boundary condition between minus infinity, at minus infinity p is 0, and at any x p is equal to p of x, I end up with the following relation, that p is equal to minus rho v0 squared times a over x cubed plus a over x to the power 6 over if you want to verify your relation, okay, we can replace back by the two boundaries we have already worked on together. We said that at x equal infinity, p should be 0. And you can verify here that if you replace x by infinity, this will be 0, and also this will be 0. Now, we already calculated together p at b, okay? We have demonstrated from Bernoulli that p at b is 0.5 times rho times v0 square. Let us verify that it is working here. We know that for b, x of b is equal to minus a. If you replace x by minus a here you will get minus 1, and here you have a plus 1 over 2, okay? So minus 1 plus 1 over 2, it will give you minus 1 over 2. And you already have a minus outside, so you get plus 0.5 rho v0 square. So your equation is making sense, okay? Any question for this problem?
Can you just repeat the last point?
Yes. After doing the integration, I got this formula. I want to verify that it's working well, because I know that at least I know that x at a, I know that at a, p is equal to 0. And I did previously, we did together calculation showing that at b, p is equal to half rho v square. I'm trying just to verify that this formula, if I replace x by the corresponding value, I will get these results. Now for point A, what is x of A? A is very far from the sphere. X, it's at minus infinity. If you replace x by minus infinity in this formula, you will have the following. Here you have minus infinity, so this term will be 1 over minus infinity to power cube. It is 0. And here also you have over x. So when you divide by infinity, it's also 0. So at x equal a, if you replace in this equation, you get p equals 0. Now to verify that it's working also for b, x of b is minus a, because if you go back to the figure, okay, this is your figure. You have x of a is minus infinity, and x of b is minus a, because b is the radius of the sphere is a, okay, and b is in the negative side, so x of b is minus a. So now you are supposed, if you replace in the equation here by x of b, you are supposed to obtain the same result of Bernoulli. So if you replace here in this equation x of b by minus a, what do you get? You get that a over minus a, it's minus 1. So it's minus 1 cube, it's minus 1. Okay? Here, if you replace, it's plus 1 over 2. So minus 1 plus 1 over 2, it's minus 1 over 2. And already you have minus outside, so it's plus 0.5 times rho v0 square. So we verified that the boundaries are working in this equation at a and b. And of course, if you want now to find the pressure at any point in between a and b, you can use the formula. Okay? Any other question on this? Okay, so let us start a new problem. In this problem, we have to determine the pressure variation in a flowing stream. Okay? So water flows in a curved path as shown in the figure, and what we want to, we can approximate the fluid here to as being an inviscid, incompressible, and steady flow. And we want to compare pressure between points 1 and 2 and between points 3 and 4. Okay? So just here we have to do comparison. It's a qualitative analysis. We don't need to find numbers because they didn't give us any numbers in the problem. We just want to know if, for example, is P1 is higher than P2, or what is the things causing increase in pressure? What are the things causing a decrease in pressure? So we will do a small qualitative analysis in this problem. First, in the course material, you have developed, you have done law of Newton in two directions, along the streamline and perpendicular to the streamline. Okay, and please pay attention. You can never switch the equations. So if you are moving along a streamline, you should use the equation for the streamline. If you are moving perpendicular to the streamline, you should use the formula developed in the direction perpendicular to the streamline, because you will have very different results if, for example, you apply Bernoulli along this line. You cannot apply Bernoulli equation when going perpendicular to a streamline. The condition, one of the conditions to apply Bernoulli equation is to move along the streamline. Okay. So now we want to compare first the pressure of point 1 and 2. Okay. And as you can see here, you have a moving fluid, and you need to compare the pressure in 1 and 2. Here you can use two chapters. You can use for 1 and 2, you can choose the previous chapter, or you can use this one. You remember, who will tell me, how can I compare 1 and 2 if I want to use the previous chapter? You remember the last part of your chapter when we did the pressure variation in fluids in doing translation? Who remember what was the function of P when I have motion of my fluid? No answer? Yalla, I'm waiting for you. You remember when we considered a flow having a certain acceleration in x, for example? Okay. Here, why you don't have ax here? We don't have an acceleration here because first you have here between these two parts, you have a constant cross-sectional area, okay? And it's a steady flow. So V will be constant along from between A and B, V is constant. Why V is constant between A and B? Because since it's steady first, okay, you have steady flow. So first it's a steady flow, okay? So because it's steady, you have that Q, which is the volumetric flow rate, is a constant, okay? And Q is equal to velocity times area, okay? And since between section A and section B, the cross-sectional area is not varying, okay? I have constant cross-sectional area between these two sections. And since it's a steady flow, so Q is constant, I can say that V is also constant. So since the cross-sectional area A is constant between these two parts, I can say that also V is constant. And if V is constant, it's not constant only, it's constant in magnitude. So here it's constant in magnitude, but also, okay, it's constant also in direction, because here, as you can see, your streamlines are moving along straight lines, okay? So I will add to this plus I have streamlines along straight lines, okay? So I can say that my acceleration is 0. Please, the idea of acceleration is very important, okay? So because in the first part of the course, you have seen streamwise acceleration and normal acceleration, okay? So pay attention for the difference between the two, because here in this problem, in this part, first you have no normal acceleration here. So here, because it's rectilinear, directly you have A normal. A normal is 0 because straight line. And because V is constant, okay, the streamwise acceleration is also 0. Because you know that how we calculate AS, so here I will put like this. You have that the streamwise acceleration AS is equal to V del V by del S. Okay? So since the magnitude of velocity is constant, so here dv by ds will be 0. Okay, so what will be the streamwise acceleration? It will be equal to 0. But keep in mind that I should also look at two components for acceleration: streamwise acceleration and normal acceleration. But since here I have straight lines, the normal acceleration will be 0. Why? Because the radius of curvature is at infinity. And you know that how you calculate A normal? A normal is calculated as, at a certain position, as V square over the radius of curvature. So if you have taken the dynamics course, you will remember that A normal is V square over radius of curvature. But here, since I have straight lines, for a straight line, the radius of curvature is at infinity. Okay? So always for a straight line, radius of curvature is infinity. So I have V square over infinity, which will give me 0. So in this
دكتور
part,
فيكي ترجع بس تعيدي أول part اللي هي steady flow V equal constant بس أول
yes,
part please.
yes, of course. When I say that I have a steady flow, this means that my volumetric flow, my mass flow rate is constant. Okay, so I will detail it more. Steady flow, so mass flow rate equal to constant. Okay, but they told me here that my flow is incompressible. Okay, since my flow is incompressible, we know that the mass flow rate is equal to what? Mass flow rate is equal to rho times Q, which is the volumetric flow rate. Okay, so the unit for mass flow rate is kilogram per second. Okay, and it's equal to rho times the volumetric flow rate, and the volumetric flow rate has a unit of meter cube per second. Okay, now since it's incompressible, because you have an incompressible flow here in the givens, I told you that it's incompressible, so you can say since rho q is equal to constant and rho is constant because it's incompressible flow. Okay, so I put here since incompressible, and normally in this course we will work with incompressible flows. Okay, so then I can say that my q is constant. So q is constant. Okay, what is q? Q is the volumetric flow rate. The unit is meter cube per second. How to calculate the volumetric flow rate? It's the velocity times the area. So v is in as you can see in meter per second, and a is in meter square. So you will get the unit of q, which is a meter cube per second. Okay, now the volumetric